Here's an example of the Arrhenius equation. We have a rate constant for a reaction that's 3.46 times 10 to the minus 2 inverse seconds at 298 Kelvin. And what we're looking for in here is the rate constant at 350 Kelvin. And we're given an activation energy of 50.2 kilojoules per mole. The other thing that we would really need here is our value for R, the gas constant, which would be 8.314 joules per Kelvin mole here. All right, so let's just write down what we know here. We've got our K1 given, so K1 is going to be equal to 3.46 times 10 to the minus 2, and that's inverse seconds. That has a corresponding temperature of 298 Kelvin. And we're looking for K2, so that's equal to some question mark there. And we know our T2 at 350 Kelvin. And we know our activation energy, and that's equal to 50.2 kilojoules per mole. Now notice that we've got in our R unit, we've got an energy unit of joules, and in our activation energy, we've got an energy unit of kilojoules. So I am going to change my activation energy to joules per mole just by multiplying by 1,000, and that gives me 50,200 joules per mole. And so what we want now is an equation that relates K's and T's in activation energy, and that, of course, is our Arrhenius equation. And so the Arrhenius equation has the form of natural log of K2 over K1 is equal to negative EA over R times 1 over T2 minus 1 over T1. Key thing to remember here is that those temperatures here and here must be in Kelvin, and since we are given Kelvin, that won't be a problem. So let's fill in what we know here. So we're going to have natural log of K2, which we don't know, over K1, 3.46 times 10 to the minus 2 is equal to our negative EA over R, so 50,200. I'm going to leave out the units just in the interest of room. And then we have 1 over T2. You really want to make sure you keep your T's and K's straight. So 1 over 350 minus 1 over 298. Okay, so we can work this out. We're just going to bring this part over here on the left. We're just going to bring that down, not do anything with it just yet. And this part on the right, we can calculate out, and it works out very nicely. We get a nice small number. We get 3.010. Now, what we've got to do now is, since we've got a natural log term over here on the left-hand side, we've got to get rid of that log term because that 3.42 times 10 to the minus 2 is wrapped up inside that function. And so we've got to use the inverse function to the natural log, which is the natural anti-logarithm, which is our e. And so we're going to do e to the natural log of that value, and that's just going to give us that value back. And then we take e to the 3.010, and you should have an e function on your calculator. We're going to take this, we're just going to move all this right up here. And so now we are at K2 over 3.42 times 10 to the minus 2 is equal to 20.29. And so now I can multiply that 3.42 times 10 to the minus 2 by 20.29, and I get a K2 is equal to 0.702, and that would still have units of inverse seconds there. Okay, notice that our value for K2 here is quite a bit greater than what we've got for K1, and that makes sense. We raised the temperature, the K should have gone up.